Hello everyone, and welcome to today's webinar, Functional Implementation of Thorough and Systematic Approaches for Fracture Examinations, presented by Dr. Tatiana Trejos, Associate Professor in the Department of Forensic and Investigative Sciences at West Virginia University. Without further delay, I will turn things over to Dr. Trejos.
Thank you for the introduction. Good afternoon, everyone, and welcome all the audience that we have today. I would like to thank for the opportunity. It's an honor for me to present today our research in physical fit examination at West Virginia University. And we are going to be talking today about functional implementation of thorough and systematic approaches for fracture fit examinations. This project was sponsored by the National Institute of Justice. And as such, we really appreciate the opportunity to disseminate the findings through this webinar and to discuss some possibilities or ways in which we can facilitate adoption to the laboratories in the near future. Before getting started with the findings of the study, I would like to take first a moment to thank all the students that have made this possible at West Virginia University. Most of them are already graduated and have been joining the workforce instead, except 2 of them. So I'd like to thank Megan, Evie, Zach, and Logan, grad students, Pedram, postdoc students, and undergrad students, Colton, Charlotte, Evangeli, Katie, and Claire Dalton. In addition to those very dedicated students that we had in this research, I would like to also take the time to thank 2 of our major collaborators, Dr. Aldo Romero from the Physics Department of West Virginia University, who handled all the computer-based algorithms and comparisons in this study, Dr. Cedric Newman from Battelle, who helped with the statistical advice throughout the whole project, FTCOE for organizing this webinar, NIJ for funding, and all our colleagues at the OSAC Trace Materials Subcommittee and those agencies and participants in the interlaboratory studies that made possible the evaluation, feedback, and fine-tuning of the methods that we are discussing today. So why are physical fits such a valuable evidence in the criminal justice system? Well, first of all, physical fits demonstrate that the compared items were once part of the same object. And therefore, they correspond to the highest degree of association that trace materials can offer. And when we can link objects with such level of certainty, it really can help with many, many different types of cases to answer important questions like what, when, how, and who committed a particular crime. In addition to that, physical fit examinations are convincing evidence. They have shown to be very relevant in many different types of cases in the criminal justice system. And also they are very easy to demonstrate to the jury and to the trier of fact. So to illustrate that, I am going to be presenting 2 cases, courtesy of my colleague Troy Ernst, a forensic scientist from the Michigan State Police Grand Rapids Laboratory. The first case is a fatal hit-and-run case that happened in the area of Northern Shore in Michigan, where near the victim, there were fairly large fragments of what appeared to be automobile paint, as well as some metal pieces. When they received one of the vehicles, suspect for participation in this hit-and-run, you can see that there was evident damage in the hood of the vehicle. So the forensic scientist was able to find a physical fit, and as you can see here in the picture on the bottom, there is a very nice alignment of the edges, of the fracture edges between item 1 and item 2. And when the examiner observed this at a microscopy level, you can see that not only that alignment is present, but also all the microscopic features are consistent between the 2 items in the top and in the bottom layer of the automobile paint. When this bottom layer is further observed under different lighting and microscopic conditions, you can now see and appreciate in a lot more detail that there were also a lot of striations that went from one side to the other in many different directions. So that provides a very convincing individual characteristics of that fracture fit that these 2 pieces were once together. In this particular case, Troy was able to find not only 1, but 3 physical fits. So in his opinion, And these paint chips originated from the hood of that vehicle that was submitted for comparison. And he also concluded that the alignment of fracture edges displayed between the question paint chips and the hood paint would not be expected except by paint that was once formally connected. And that's what we call fracture match or fracture fit. So you may be asking why we need to do then further research when we have evidence that is so self-convincing. And the reason for that is that even though this evidence is very easy to demonstrate, we still need to have scientific solid foundations to demonstrate what is the criteria that help us to arrive to those conclusions and to demonstrate that having random physical fits are very rare. In addition to that, not all the cases are that straightforward, or sometimes we don't have all the criteria to make those important calls. So to illustrate that, I'm going to be talking about a second case that Troy did. This is a motor vehicle theft, and it has 3 items that were submitted for comparison to the laboratory. The first item, item number 1, was recovered from the hitch of the suspect vehicle. Item number 2 was recovered from the stolen motorcycle. And item number 3 were recovered from the suspect dolly in the vehicle trailer. And this one has 4 different straps that correspond to that third item. So in this particular image, we are showing an example of the general class characteristics that we are observing in sample 2 and one of the samples 3. But you can see that at the edges, there is not an alignment. So this is an example of a non-fit determination. These 2 other images are examples in which there are corresponding alignments between the straps of items 2, different items 2 and 3. And as you can see that even some corresponding lines indicate alignment angles between these ones. However, in this particular case, the examiner concluded that regardless of the alignment, the comparisons were limited by the clarity of the strap ends, the construction of the straps, and the difficulty in documenting some of the alignments, and the lack of rigidity in the fibers and the yarns. So the conclusion in this particular case was a high degree of alignment, but there were not enough features or foundations to document this as a physical fit. And this is where really this research come along to help forensic practitioners to develop criteria to determine what are individual characteristics that can help to determine when the features are good enough to call a physical fit and understand the type of error rates that we encounter in these particular materials. So the first thing that we did as a research team was to discuss with the forensic practitioners and the community what else is needed to further support such a valuable type of probative evidence like physical fits. And the main thing that we determined is what are the current needs? And to understand that, we first focus on who are our customers, the jury, the judges, the lawyers, the community as a whole. And most importantly, what are the expectations? Because they will be expecting this type of physical evidence that is highly probative to be presented with solid scientific foundations and statistical criteria. So with that, we identified 3 main needs at that time: objectivity, consensus, and scientific reliability. In terms of objectivity, we have the situation with physical fit examinations that they depend entirely on the human judgment. And subjectivity is not always a bad thing, but they can be risky if we don't have standardized criteria. Which brings us to the second aspect, which is the need to develop more consensus protocols in what constitute an individual characteristic, whether or not that changes by material type, the standardization of that criteria, what is good enough for calling something a match, and develop standard methods and systematic peer review processes. And finally, being able to report error rates and most importantly, understand what factors may affect error rates and have empirical demonstrable basis to assess the significance of fit examinations. So we focus on those 3 aspects in this research, and then we decided to take this with an approach in which we wanted to work towards standardized practices and common languages, And we started with three main materials as well, were determined through a survey that are the ones more commonly submitted to forensic laboratories for physical fit examination: tapes, textiles, and automobile polymers. So we work very closely with practitioners during this research, and we also established multidisciplinary collaborations in our team. So we were a team that consisted in forensic scientists, computer scientists, statisticians, human factors, and work together to develop standardized comparison criteria and evaluate the error rates and the applicability of these methods. So how can we use physical fits evidence to its full potential? So the main objective of this research was to strengthen the field of physical fit examinations by demonstrating the scientific validity and developing standardized, systematic, reproducible, and quantifiable comparison criteria. And we did that through three main stages in the research. The first one was to establish what was the criteria for evaluating and reporting features that were important for each particular material. Then develop a systematic and quantifiable metric that can support and complement those observations. And finally, design a large population data set and interlaboratory studies to evaluate error rates. In this presentation, I'm going to be talking a lot about some statistical evaluations that we did, but I just want you to bear with me in the sense that those statistical evaluations were necessary to demonstrate that scientific validity, but keep in mind that the end product, what could be applicable in the laboratory, is really a simple, adoptable method. The statistical evaluation was necessary to provide that foundation. So we are very proud that we created the largest physical and digital database ever created for physical fit examination, with more than 9,000 samples consistent of different types of duct tapes, fabrics, and plastic polymers, in particular automobile plastic parts. So I'm going to start talking a little bit more about duct tape and walk you through the process of the research, and then we're going to jump into textiles and automobile plastics. So the first step for the research was to develop and validate a systematic approach that helps us to assess the quality of duct tape physical fits. And what was really important from the beginning of this study was to develop a method that was easy to incorporate in the current examination workflow of physical fit examinations. So indeed, we followed the same steps that now are established through an ASTM method for a standard guide for forensic physical fit examination that was developed through the OSAC Physical Fit task group. That consists in three main steps. First step is to observe the general features. If there are exclusionary differences at this stage, then we report an exclusion and no physical fit examination is necessary. If at this stage there are no exclusionary differences, then we assess the suitability to see if we can continue with physical fit examinations. Second step is observe and compare the features at a macroscopic level, and then if necessary, continue to the examination to the third step in the microscopic level. So what is really new in the research that we developed is that what we are doing is only incorporating standardized terminology and criteria on each of these steps, and systematic and demonstrable documentation in each step to make it more robust. So how does it look like, these steps for duct tape? So the first step in duct tapes, we do just a general evaluation of the common class characteristics to evaluate whether or not we have exclusionary difference at this stage. And if not, we compare first the question, then the non-sample, and evaluate general alignment on the edges and report that. Then the second step consists of the macroscopic assessment of the features that can derive a fit or non-fit determination. And what we decide here is to split this tape into 5 equal size sections and document features that we're going to describe in a moment on each of those 5 sections to determine if there is alignment and distinctive features present. And then finally, the third step is to evaluate those same features, but now at a microscopic level. So the main question that we have for any material was, what is the smallest unit of comparison that we should use at the microscopic level? So in the case of duct tapes, that decision was made by utilizing the fact that the screen counts or fibers in duct tapes are very consistent along the whole roll of tape. So we decided to use the smallest units of comparison as the distance or the area between every two screen fibers. In order to do that, it allows to do this in a very systematic manner and facilitates a lot of the documentation and then go back to that. In addition to that, we are going to be making decisions on the qualitative features for every screen area and make decisions of every beam independently of whether or not this could be a fit and non-fit on an inconclusive beam. And based on that, we then calculate a quantitative metric that helps us to determine or have a sense of the quality of that physical fit. So for step 2 and step 3, which is the macro and the subunit assessment, the first thing that we developed were identify which features are the most informative for examinations of duct tape. And we came up with 9 different features that we are going to be documenting and reporting in a simple Excel template that has auto-populated cells, so that help us to auto-fill those requirements as we are observing each of those. So let me walk you through how these features look like. The first feature that we document is whether or not there is alignment of the edge pattern morphology. So self-explanatory. In the left-hand side, we're going to have the ones that are indicative of a fit, also in a green frame. And in the right-hand side, the ones that are indicative of a non-fit. The second feature that we report is the alignment of severe dimples. Dimples might be present due to manufacturing processes or not. So in this particular case, we are going to be reporting whether or not they are absent or present. And if they are present, whether or not they are indicative of a fit, like in the case here on the left-hand side, or indicative of a non-fit when there is no alignment of those dimples, like the example in the right-hand side. The third feature is calendaring striations across the edge. So again, those striations could be indicative of a fit if they go across from one of the fragments to the other, or indicative of non-fit when the striations are truncated or not present and present in only one of the sides of the fragment. Macro alignment of warped screen on the adhesive side is also quite important, and they can be indicative of a fit when they align or otherwise indicative of non-fit. Especially when we have hand-torn separation, it's not uncommon to see protruding warp yarns like the one shown in here on the left-hand side that leaves some empty spaces that can be easily aligned with those materials. When there is corresponding of those protruding warp yarns between one side to the other, that is indicative of a fit. And when we have extra material or not corresponding with that, that is indicative of a non-fit. Next, continuation of the screen with pattern, like the example provided here, near the edge of the two fragments that we are comparing. Sorry. And the next one that we document is whether or not we observe distortion on the edges. When we observe distortion, we can document whether or not that distortion is explained by observed stretching directionality that is present and consistent between the two fragments that we are analyzing, and that can happen in the backing side as well as in the adhesive side. So in this particular case, we document whether or not we observe that correspondence. Web screen near or at the edges that are consistent or not consistent with the overall pattern, that help us also to determine those important features to evaluate whether or not that can help us that is indicative of a fit or non-fit correspondingly. And finally, we also document whether or not we observe any missing material on those areas that we are doing the comparison, and that is documented in the template. Then we move to the next step, which is making the observations of those same 9 features, but now at the microscopic level in each of the screen units. And the advantage of that, as I mentioned, is that we can document whether or not for every being independently, we observe a fit, in which case we'll put a 1, a non-fit, in which case we'll put a 0, or inconclusive, in which case we'll put a 0.5. And then automatically the template will calculate the percent of matching areas, which will be a score that ranges from 0 to 100 to give us an idea of the quality of that physical fit. This provides an opportunity to complement those qualitative observations by doing a systematic documentation that is also quantifiable, reproducible, and also easy to do peer review process. So this is how the template will look like. And as I mentioned before, we will have auto-fill cells that we just click and put the observations in there. And what the analysts will need to do once they analyze each of the screen areas separately is enter what we call an area fit code, that 1.0 or 0 that I mentioned earlier for each of those beams. Something simple that we implemented in this Excel template is a macro in which when you enter a 1, it will color code that cell automatically as green, 0.5 as a yellow, and 0 as red. And what that helps is to really bring in a matter of seconds an observation at a glance, in which we can see very easily across the width of the tape, which are the matching and non-matching areas. The template will automatically calculate the edge similarity score for you. And then in conjunction of that score and all the observations that are documented in the template, the examiner will write their opinion or conclusion at the bottom of the form. The use of these color-coded visual aids for edge calculations are very helpful for training and for peer review process when we want to do verifications of the observations. It will also help us a lot to determine where or when we have particular inconsistencies and go back directly to that cell and the observations of our thought process that are documented and imprinted in that template. So this shows an example of a fit with high score and inconclusive in the middle, and how a non-fit may look like. This has become very handy as well when we do inter-examiner comparisons. So the next step was how well this method and documentation template works and what factors can influence the error rate in this type of examinations. So we produce 4 different publications, and if you are interested in having access, some of these ones are open access, but reach out to me and I'll be glad to provide those copies for you. In the case of duct tapes, we created a database that consisted of over 3,000 duct tape comparisons that were assigned random IDs and were providing always blind to the analysts. They didn't know whether what they were examining was a fit or non-fit, to prevent any bias. And the data set consists different combinations of to evaluate the effects of separation modes. So we did hand turn versus scissor cut, different qualities of tape. So we did medium, low, and high quality, and stretch or distort versus more pristine samples to simulate more typical stretching and distortion observed in casework. So the first step was evaluating the distribution of those scores across all the different data sets that I described. And one way of doing that by exploratory visual observation is shown here using box plots. So what we have here in the x-axis is the score that goes from 0 to 100. And then in the y-axis, you will see box plots that document the distribution that the examiner provided in terms of those scores to the different data sets. So we have here 9 data sets from top to bottom. We have 3 low quality, 3 medium quality, and 3 high quality in the y-axis. And for each of those, we have scissor cut, hand torn, and hand torn stretch. So what we can see here is that in each of those sections, the top graph represents the values observed for all the hundreds of samples on each data set for the true non-fit samples. And the one in the bottom represents the respective results for the true fit data sets from each of those samples. So the first thing that we learn about these distributions is that the big majority of the true non-fits receive scores lower than 20 consistently, and the big majority of the true fit samples reported values above 80, providing support to the true fit for a high quality fit association. The other thing that we notice is that there is very little overlap between true fits and non-fit, and that helps a lot to determine that this is a good assessment of the quality of a fit, with very few exceptions. So I want to bring your attention to the bottom of the graph. Those represent the high quality hand torn and high quality hand torn stretch. What you will see on the right-hand side is that the true fit samples had a very large spread of those box plots, representing a lot more variability than the remaining of the data sets. And the reason for that, we learned based on this study, is that with the high quality hand torn, which is the figure here that hopefully you can see my mouse in the middle, what we notice is that when we do hand torn or high quality tapes, they tend to provide very straight separation lines with very non-distinctive features on the edges as compared to other features that we're imparting in the other type of quality tapes. And that provided a lot more variability in the features that we were observing in true fit samples. So this is what we are observing here with these wider box plots in those two data sets for the high quality hand torn. So when we evaluate these in terms of performance rates for all the different data sets, what we can see is that there were very high true negative rates and very high true positive rates across all the different data sets. Most importantly, we also had very low false negative rates and very low false positive rates. Indeed, in the hundreds of samples that were analyzed by different examiners, we didn't find a single case of false positives, which is critical in this case of physical fit examination, because that's one of the main assumptions that we make. That is very rare, very rare to find an association on a physical fit just by chance. False negatives were also very low, with the exception of the hand torn high quality sets, as I mentioned earlier, for the reasons that I described. So you can see that those error rates are significantly higher because we observed less distinctive features in the true fits. Overall, they provide very high accuracy across the different data sets. And most importantly, when we did inter-examiner variability, so two examiners analyzing the same data set, completely blind to each other and independently, we observe identical results and very high correspondence. So the next step was to evaluate these at an interlaboratory level. So we provided the distribution of interlaboratory samples to 38 participants that kindly donated their time and dedication on that. We submitted samples that were casework-like, representing items. And we submitted 3 kits simultaneously to different laboratories. Each kit contained 7 samples that the examiner were analyzing, and we evaluated that through a pre-distribution consensus panel to make sure that each kit had in the respective samples similar scores and edge morphology. Each laboratory therefore received 7 samples that were blind to them. They didn't know whether or not they were the ground truth a fit or non-fit. But their corresponding ground truth is that 3 of them were non-fits with low scores. 3 of them were fits meant to be with high scores. And 1 of them was also a true fit, but that has a more challenging lower score in the upper 7s score. So for the sake of time, I'm going to just present the results for the second interlaboratory in this table, but they were very similar. Accuracy, as you can see, is very high. Most importantly, again, we didn't have a single instance of a false positive reported based on those scores, and very low false negative rates. Most importantly, this graph here again shows the box plots of distribution of scores represented by each laboratory participant for each of the 3 kits. And what we can see here is that we observe a lot of consistency across the reporting of those scores between participants, with the non-fit of every kit having lowest scores below that threshold. The high fit of high score fit represented here in green also was very consistent across the participant. And the one that was a difficult fit also received lower values as expected across all the different participants. Also important is that with the documentation, as I mentioned, that visual observation is very helpful to determine whether or not we have consistency across the different laboratories. So this is an example for one of the samples for the difficult fit lowest score for the first interlaboratory study. And you can very quickly see across all the different participants that the majority show like inconsistent or inconclusive areas in the screen counts between 25 and 36. And when we look at the tape itself, you can see that that's the area that presents more distortion. So again, these can help us to determine why, if there are some inconsistency, what was the rationale for the examiner to put that particular score to a given comparison pair. So we receive a lot of feedback that really help us to incorporate many improvements in the methodology. And one of them came from a question from one of the participants that said that they often receive samples that are not fully complete in width. So they wanted to know if there is a way that we can investigate how much sample loss is necessary so that is then no longer suitable for comparison. So instead of having a full question sample, what happens if I'm missing a portion like that, or even getting to only like 1/3 or 1/10 of that sample? When we will be able to determine that that small sample is no longer suitable for comparison. So we give this a little bit of thought, and we decided to use the template and all the reporting scores to address this question. So what we did is that we took the hundreds of samples in which we have documentation for all the beams areas and start automatically with a random assignment, selecting portions of that tape to evaluate what would happen if we only have a particular portion of that tape. So this is one of the worst case examples that we found. This is an inconclusive case that had a score of only 43. So you can see a lot of non-fit and inconclusive areas. So if we only take 10 out of 30 beams in this particular example in this area on the upper part, that will give us a score of 20, and the conclusion will be a non-fit. If we, however, take the bottom part where there is some alignment, that will give us a score of 80, which would be supportive of a fit. So that represents a worst case scenario, and we evaluated these hundreds of times to evaluate how the accuracy could be affected if we only have a partial sample for the question item. And these graphs here represent those results. So in the left-hand side, we have the results for the low quality set. And in different colors, we have the hand torn and the scissor cut. So what we have in the x-axis is the percent of the sample coming from 100 all the way to 10% as we reduce the number of the size of that sample. And then on the y-axis, you can see how that accuracy was affected. So what we were able to determine, if we want to maintain the accuracy to at least 90%, we need at least 35% of that portion of the sample to make those determinations before the error rates start decreasing a little bit further. In the case of high quality, which is the right-hand side figure, we can see that the scissor cuts had a very, very high accuracy regardless of the portion of that sample. So the uncertainty increases a little bit more when we start in about 35% of that sample. And however, in the high quality hand torn, you can see, if you remember, that the false negatives are much higher due to the variability of those patterns. And so what our recommendation is, when you have high quality hand torn materials of tape, not to use partial width. If you have high quality hand torn and a partial sample, our recommendation is to conduct a chemical analysis instead, just to be in the safe side. But you can see that the error rates can go lower, or the accuracy lower in the 70% range. Another question that was very interesting from participants was if there was a means for the examiners to evaluate how much weight they are putting in that decision for the different features. Because remember, for every bin, they will evaluate up to 9 features, and then based on that 9 features, determine whether or not that bin is a fit and not fit. And we'll do that independently for every bin. So we use some mathematical algorithms to extract the information from those reporting templates, and we learn very interesting things. We learned that the separation of the features that are more relevant or have more weight in that decision not only are dependent on the quality of the tape, but also on the separation method. So this is an example of how that can be read. And in the bottom, we have an axis that represents the weight of importance of that feature in the determination of that particular fit not fit decision. And then in the color black, we have the hand turn. In the blue, we have the scissor cut results. So what we can see is that for scissor cuts, the most important feature for determining a fit was the web screen pattern, followed by the alignment of severe dimples on the tape backing. However, for the hand torn, even though the web pattern was also important, the dimples were not as important. And when we went back to evaluate the data and the information and the images, we noticed that most of those dimples are going to be also present in the area where the weft is located. So when we do hand torn separation, it's very unlikely that the separation will occur across those dimples. So it's was very, very rare to observe in hand torn dimples that are severe. In the case of scissor cuts, that was a lot more common, and when present, that provided a very important distinctive feature that the examiner provided a very high weight to that. We also did computational models using machine learning algorithms and showing thousands of images to the algorithm using computational networks to learn about the data and identify automatically what are those features that are representative of a fit and non-fit, and that produce a probabilistic output of whether or not this is a fit or not fit. Interestingly, we were able to see that the machine learning model, which is presented here on top, versus the analyst examination results were very comparable in terms of true positive rates and true negative rates. The algorithm also has a feature in which it can highlight in the output the areas that the algorithm places more weight in the determination of a fit and non-fit and color code them. And then we can compare those to the examination and annotation that the examiner does in the template. And we were able to demonstrate and to find that the computational algorithm comparison criteria was strikingly similar to our rationality thinking process that we document in the Excel template. So this method provides quantitative and qualitative measures of the quality of the physical fit that has a very high overall accuracy and thorough and transparent documentation, which in our opinion is one of the most important take-home message from this study. Also, the use of modeling allows answering additional questions that were posed from examiners to us regarding the partial edge in the case of tapes. We recommend at least 35% to still hold value for that comparison. And they also help us to determine the most informative features and learning that they vary by quality and separation method. Moving into the textiles, we were interested in evaluating different aspects regarding separation methods. So we use hand torn and stabbing, different compositions, fabrics, different construction, including knit and weave, and different designs, what we call unicolor, multicolor, which can be observed with different patterns and colors that we use on the image on the right-hand side. So we evaluated over 1,000 samples, comparisons of fabrics. And although I don't have time to go over into a lot of detail on the features, this was one of the most important steps. Again, standardizing which features are the most informative in the case of textiles. So we chosen 8 of those to provide in that documentation template. In terms of performance rates, here on the top, on yellow, we are presenting the results for stab samples, and in blue in the bottom, we are presenting the results from the hand-torn pairs. In general, what we observed is that the false negative rates were very low, and overall, we obtained very high accuracy in both data sets. And although the false positive rates were also low, they were not zero. And that was a very important finding in the case of textiles because we were able to determine that there are certain factors that can produce these error rates, and it's important for us to know what they are. So what we can learn from the box plot, again, we have very good separation between the true fits and non-true fit samples with very good separation of those scores. With the exception, again, of two data sets that have a lot more variability in those true fit scores, which is the knit samples, whether they are unicolor, multicolor, when they are hand-torn. They provide a lot more distortion, and therefore those scores get a little bit more wider and a lower values. We did also an interlaboratory study. In this case, we submitted 3 samples. One was a fit with high score, a fit with lower score, and finally a non-fit. And we submitted images where they can zoom in and look at all the different details of features in each of the beam comparisons. In the case of this study, we also had very good correspondence between the different laboratory participants, which the non-fit samples receiving very low score and the true fit sample receiving correspondingly the scores that we were anticipating with the pre-distribution. So a lot of good agreement between laboratory. So moving into the automobile polymers, which shows different types of plastics that are encountered in automobile vehicles, and determined, in this case, 10 different distinctive features that were found to be the most informative when we do those physical fit examinations. Again, we use the same principle of having a template in which we automatically can select the populated cells to evaluate those 10 features. But we did something different here. In addition to the ESS score, one of the questions that we have from the participants is if we could have a mean in our template to add an option in which the examiner can determine from all those features evaluated which one holds the most weight for their decision to put the fit non-fit decision in a particular beam. So we call that feature prominence value, and we did it in a very simplistic way. We did a scale of 5 that goes from 2 to -2, passing for 0, which is inconclusive. So a higher value will indicate that that feature is highly distinctive or indicative of a fit, and the -2 represent that misaligns and is highly distinctive, indicative of a non-fit. So at the end, we can also add those feature prominence value and obtain an overall score that we call FPS, or feature prominence sum, that is indicative of the overall quality of that fit. It helps in addition to complement that for the final decision. In terms of accuracy, we obtain, again, very good accuracy. Like in duct tapes, we didn't find any single false positive in these data sets. And most of the error rates were coming from either through false and negative results or inconclusives from samples that were distorted a lot during the breaking process. So here are the examples for the similarity score that are in the left-hand side as box plots or as a frequency tables. But what we can see here is a very, very striking separation between the values observed for true non-fits and true fits. And when we look at the FPS instead, Those distributions give us a little bit more of a scale, helping us to determine the value or the level of weight in those features that we were evaluating. So when we use FPS, what we can see in the hundreds of samples that were evaluated, this is the distribution of the scores. True negatives obtain results that go from -5 to -40. True positives obtain scores from 15 all the way to 55, and the higher that value, the more distinctive features were observed. And inconclusives consistently had values between 0 and 10. So these could correspond to a complementary metric that we can use in addition to the ESS and the qualitative features that we include in the template. So in conclusion, what we propose is, these methods can provide a simple approach for physical fit examination that are not meant to replace the way that we do physical fits, but rather complement and modernize current practice with a more systematic way of documenting and with more systematic criteria to identify those features that are important in every type of material. Most importantly, this allows transparent demonstration and peer review process that can be used for training, for presentation of the evidence, and assist with blind independent verification reviews. Both the qualitative and quantitative descriptors that we use in this documentation has helped to develop demonstrations for the scientific validity through performance rates and other factors that we're evaluating. So main lessons learned is that material type matters. Physical fit performance vary by material. So it's very critical to identify what are the significant features for every material. Error rates are very low and very unlikely to observe false positive, but it's fundamental to know factors that may affect those error rates. And finally, documentation is key. Systematic documentation of that top process adds a lot of transparency, consistency, and minimize bias. So we were able to narrow down all those gaps that we discussed earlier in terms of objectivity, consensus, and empirical demonstration of the validity of physical fit examinations. Again, the statistical evaluation helped us to evaluate performance rates from very large population studies, interlaboratory testing, computational models, and created databases, physical and digital, that are now available to the wider community. And the end product is simple adoptable methods that only require documentation through this Excel tool that I mentioned, and that helps to demonstrate the thought process that can be evaluated through technical review and verification. So what will be required for method adoption, which is our intended next steps? And really all that is needed is training on that Excel template and implementation so that we can imprint the thought process of the examiner during this type of examinations. And in terms of equipment, is everything that you use in the laboratory, just a microscope, the Excel template, and being able to document that thought process. So 3 easy steps: identify the distinctive features by material, document them using the systematic reporting document at the macroscopic level, and provide that documentation as part of your records. So with that, I would like to again thank everyone who has made this possible. And if your laboratory is interested to exploring this in a more detail, evaluating potential adoption or pilot plans, or how modification of these templates could be implemented, please feel free to contact. So thank you very much.
Well, thank you for providing such an informative presentation, Dr. Trejos. I am John Grassel, the co-PI for the Forensic Technology Center of Excellence, and we will now begin our question and answer session.
Thank
Our
you.
first question from the audience is, for the cross-laboratory testing, what kinds of labs participated and what kind of training did the participants have?
Thank you for that question. That's a very interesting question, because unlike other interlaboratories that we conducted, in those interlaboratory studies, the laboratories already do this in casework. This was an exception in the case that they were testing a new methodology that was not implemented in the laboratories. So what we did was a virtual training, like a kind of mini workshop in which we explained all the features in a lot of detail, and then we went step by step in how to utilize the reporting template. And that helped a lot with the understanding of how to use that. So the participant laboratories, we have 38 different laboratories across the United States that participated in the first and the second laboratory. And most of them were trace evidence units that commonly do either textile or duct tape examinations as part of the physical fit assessments.
Wow, that was some great participation with the 38 laboratories.
Yeah,
So
we were
thank you
very
very much.
lucky of the, yeah.
Our next question is, could you please tell us how many features or individual characters you see for physical fitness, for physical fit with confidence?
With confidence. I'm not sure if I understand correctly the question. But what I get from the question is like, how confident are we on the features that we selected? So the features that we selected were based on a preliminary assessment of known true fits and true known fits to observe how informative were each of those features. And then the final tests, I would say, to evaluate how good those features are in the physical fit examination is to really evaluate that through the blind larger data sets and evaluate how the combination of these features will provide certain levels of error rates. So we reassess and fine tune based on those observations. I hope that answers the question.
I think it does, and if not, if the questionnaire wishes to pose it in a different way, please do so. Thank you so much. Next question, and I'm sure this multiple people would have this as well. Is the Excel template you presented, is that available for a download?
Absolutely. Please reach out if you want to test it, if you want to evaluate it, if you want to discuss it, fine tune it, adapt it to a laboratory, please contact us. That's the main idea of this feature. We want to make it as simple as possible, but in a way in which really can help that process that you're already doing in the laboratory, but now imprinting that thought process and all these steps in one single document that you can assess, especially if you need to go and testify in the courtroom and you are going to be doing this 2-3 months after you did that case analysis. It becomes very handy to have the documentation about what did I see at that time when I was doing the examination that provides those foundations for my opinion. So yes, please reach out to my email.
Thank you.
Be glad to that.
Great, and we will put up Dr. Trejos's email again right at the end of this presentation, so thank you. Our next question, so we talked about a lot of labs participating in the study. Have any labs adopted the technique yet?
No, that I know. We just relatively recently finished this grant project. So our idea is to have follow up with the community. And again, if you feel that you are interested or just want to explore a little bit more, learn a little bit more, feel free to reach out. We will be more than glad to work with your team and evaluate whether or not this will be something that could be feasible to try in your laboratory.
Great, thank you. Next question. Has any research been conducted, to your knowledge, on electrical tape?
So there has been some preliminary studies that were done, if I recall correctly, maybe 10 years ago, with some, I think it was the FBI, for example, did some studies on electrical tape with small data set, but with different participant laboratories to evaluate potential error rates. We haven't done yet electrical tapes, but there is a lot of possibilities to implement some of these features, just adapt the features that are relevant, because electrical tape is very different to duct tapes. And the features that we are observing are in a much reduced space in the first place. And second, electrical tapes tends to be a lot more stretchable. So it will be something very interesting to evaluate what are the error rates. It's something that we have in future work, but we haven't done it yet.
Great. Yeah, definitely some possibilities for future exploration. I think in that area, you're correct. Our next question is, how do you decide on the number or size of bins for non-duct tape samples, for example, polymers?
That is a great question. And the answer for that one, we were very lucky in the duct tape to have something in the material per se that allows us to do that in a very, very systematic manner with the screen areas. In other materials, including textiles and polymers, we don't have that luxury. So we made more like practical solution or decision of using 10 bins in that area. So if whatever is the size of that fragment that we are examining, we split it into 10 or 5 equal areas, depending on the size of the fragment. And then we evaluate those features in those subunits. But that could vary, and this is the beauty of this kind of template. You can really adjust it in a case-to-case basis, because if we have, for example, automobile polymers, we observe that sometimes we have fragments that are quite small, less than 1 inch, right? So doing more than 10 areas will be going into much lower detail than we really needed. But sometimes we can have something that could be like 1 feet or longer, right? So if we do a lot of small areas, that will be impractical. So in this particular case, we decided to use 10 different comparison areas or 5 different comparison areas, splitting that into equal sizes depending on the size of the polymer. The important thing here, whether it's 10 or 20 or 5, is to select an area that would allow you to see those features at the macroscopic and microscopic level without going too wide that we are losing those microscopic features, or too small that we are really getting into a lot of variability that really dilutes those informative values. So it was more like a decision based on practicality of the application in polymers.
Great, thank you. Our next question, is there a minimum number for ESS or FPS to report a true physical fit?
Yes, that's a great question. So based on the large data set that we evaluated, and regardless of material, what we observe is that when we get a score of 80 or higher, we got a very strong support of a fit. So in other words, we never saw a score of 80 or higher that will provide the wrong conclusion. And for true fits that have very distinctive feature, that was the score that we recommended. So our recommendation is when we have very low scores, those are a strong indication of a non-fit. When we have a score of 80 or above, that's a very strong support for the fit conclusion. And if you have 80 or below, our recommendation is to report, let's say from 80 to 60, high level or high degree of alignment, but not necessarily a physical fit, because you are losing at that point for many different reasons, distortion or whatsoever. You are losing important features that are not allowing you to determine with high certainty that quality of that fit.
Well, thank you so much, Dr. Trejos, for your time today. And unfortunately, we do not have time to answer all the audience questions. But as we remarked earlier, please feel free to reach out to Dr. Trejos for additional information if we did not have time to answer your particular question. Thank you so much for attending. And thank you again, Dr. Trejos, for being with us here today.
Thank you very much. And please feel free to reach out to answer any follow-up questions. Thank you.
As you depart, we kindly ask that you take a minute or two to complete our post-event questionnaire. The link will be pasted in the chat and also appear as you exit the Zoom room. Your feedback helps us improve our outreach efforts and continue to provide the best experience possible. Thank you again for attending, and we hope everyone has a great day.